We're still looking at solving polynomial equations, and so we looked at it by factoring. We looked at solving equations where the variable was underneath the radical. What we want to look at now is where we have equations that have fractional exponents. So we have 5x raised to the 3 halves minus 25 equals 0. Well, let's talk just a minute about what we mean by a fractional exponent. If you have a number, raised to the a over b, this means that we're talking about taking the b root of x raised to the a power. Or we could look at it this way. It's the b root of x raised to the a power. Now the difference in these two is just the order that you do things in. Taking a root and raising to a power at the same level of our order of operations. So this first one means that we raise to the power first and then take the root. This one means we take the root first and then raise to the power. An example, we could have 8 to the 3 halves. Now remember, the denominator tells you the root that you're taking. So let's make that a little bit different. I meant to be 8 to the 2/3 would be a little bit easier to work at this stage. So 8 to the 2/3 power. So the denominator tells you the root you're taking. So we're talking about taking the cube root of 8, and then let's square that. Well, the cube root of 8 is 2, and 2 squared is 4. Now, if we did it the other way, then we're saying we want to take the cube root of 8 squared. Well, 8 squared is 64, and the cube root of 64 is 4. So we get the same answer either way. So it kind of depends. Normally it's easier if we take the root first. It gets our numbers down a little bit smaller, and it's a little bit easier to see what that root is if you can take it when your number's smaller. But this is what we mean by a fractional exponent. And so if you think about it, then the square root of 25 could also be written as 25. We're taking the square root, we're raising it to the first power, so 25 to the 1/2. And so those are just some things with our fractional exponents and what they mean. So what we want to do is we want to solve this. Now we're going to solve this using that same idea that we did with our square root principle. We're going to get our variable by itself, so I'm going to add 25 to both sides. Going to divide by my coefficient so that I have just my variable alone. So I end up with x to the 3 halves equals 5. Okay, when we start solving, remember we raise it to the power as the root that we're taking. But in this case, we're also cubing that answer. What we want to end up with is an exponent of 1. We want to end up with x to the first. So we want to multiply 3 halves by something so that we end up with 1. Well, that gets us back to our multiplicative inverse property, that when you multiply reciprocals, you get 1 for the answer. The reason we're talking about multiplying is because of our rule that when you raise to a power, you multiply the exponents. And so that would be x to the AB. So we're using a lot of our exponent rules. We're also using our multiplicative inverse property. So we want to raise this to some power, and we want to end up with x to the first. So that means we want to raise it to the reciprocal power. And if we do something to one side, we're going to have to do it to the other. So we get x is equal to 5 to the 2/3. Now I can't simplify 5 to the 2/3. I cannot take the cube root of 5 and it come out exact. And so we could leave it this way. A little bit better way to leave this, if you wanted to put it in radical form, would be saying we want the cube root, but we can square 5. So we want the cube root of 25. If we look at another one where we have a fractional exponent, say that we have x to the 2/3 minus 8 equals 4, equals -4. Okay, we want to get our variable by itself, so we're going to add 8 to both sides. -4 plus 8 would be +4. We want to raise this to the reciprocal power because we want to end up with an exponent of 1. And if we do something to one side, we have to do the same thing to the other. So we get x to the first. Now here we can do some simplifying, and we can choose the order that we do this in. It's a little bit easier if you deal with the root, and if you wanted to just write it with a radical, it's going to be the square root of 4 cubed. Well, so we could cube 4 and then take the square root, or we can take the square root and then cube. Well, the square root of 4 is 2, and 2 cubed is 8. If we had cubed 4 first, it would be 64, and the square root of 64 is 8. So we can go back and we can take the root of these in the same way that we did our square root problems, or the square root property. Okay, we also want to look at solving equations that are in a quadratic form, but they're not quadratics. But they can be written in the form of a quadratic, and we're going to do that with substitution. If we start out with the equation x to the 4th minus 5x squared plus 6 equals 0. Now this is not a quadratic because it's not a second degree equation. But if you notice, if I look at my x squared and I squared it, I would get x to the 4th. So this is in the form of ax squared plus bx plus c. Because if I took this quantity and squared it, I get this one. So we're going to solve it like a quadratic even though it's not. Now the process we're going to do is we're going to say, well, let's let u be equal to x squared. We're just going to pick a whole different variable. We're going to let that be equal to the x squared. Now, if we squared both sides, we'll get u squared, and x squared squared is x to the 4th. If we just simply took this and squared both sides, and so there's our x to the 4th. So what we can do is for x to the 4th, we'll substitute in u squared. For x squared, we'll substitute in u plus 6 equals 0. Now we have us a quadratic equation, which we know how to solve. In fact, we can factor this one. We want factors of 6 that add to be 5. Well, that would be 2 and 3. The signs are the same because we added them, and they're both negative. And setting each factor equal to 0, we get u minus 2 equals 0, and u minus 3 equals 0. So u equals 2, and u equals 3. Well, that works out really nicely. But we don't want to know what u is. We want to know what x is. So now we're going to substitute back in. U was equal to x squared. So x squared equals 2. Then taking the square root of both sides, we have to remember that plus or minus. We get that x is equal to plus or minus the square root of 2. And x squared equals 3, so we'll take the square root of both sides, remembering the plus or minus, and we get that x is equal to plus or minus the square root of 3. Since this was to the 4th power, there should be 4 answers. And so we have 1, 2, 3, 4. We have all 4 of our answers. We're going to look at another one along this line that can be put in that form. Let's take the equation 3x to the 2/3 minus 11x to the 1/3 minus 4 equals 0. Well, this kind of looks like a quadratic maybe. Now we always start out, we're going to let u be our middle term. So let's let u equal x to the 1/3. So we want to know, we want to square both sides. That's going to be x to the 1/3 squared. Now remember, our property says when you raise to powers, you multiply your exponents. So 1/3 times 2 is 2/3, which is our variable for our first term. So we can do this then by the substitution. So x to the 2/3 is equal to u squared. X to the 1/3 is equal to u. Minus 4 equals 0. Now we could do this by, or we could try to do this by factoring, but usually if I have a coefficient other than 1, I just go ahead and use my quadratic formula. So u is equal to the opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2a, which would be a positive 11 plus or minus the square root of 121 plus 12 times 4 is 48 over 6, which is 11 plus or minus the square root of 169 over 6. Well, the square root of 169 is 13. So now we have two different answers. U is equal to 11 plus 13, which would be 24 over 6, or U is equal to 4. U is equal to 11 minus 13, which would be negative 2 over 6, which is negative 1/3. But we don't want to know what u is, we want to know what x is. So u is equal to x to the 1/3. So now we're going to replace u with x to the 1/3 equals 4, and we'll solve that by cubing both sides, raising it to the reciprocal power. So we get x is equal to 64. Here, x to the 1/3 equals negative 1/3. So cubing both sides, we get x is equal to negative 1/27. So those are our two answers for what x is. So it's a matter of seeing if it can be written in the form of a quadratic. You take what your middle term is, and then you square both sides. You let that be what your u is, and then you square both sides to see if you got your first term. If you did, then you can substitute in, solve it like a quadratic, and then you can substitute back in at the end. The last section that we want to look at today deals with absolute value. And so we're going to look at solving our absolute value. Now what we mean by absolute value, it's our distance from 0, but the absolute value of 36 is 36. That's how far that number is from 0. The absolute value of negative 36 is also 36. It's 36 units from 0. It's just going to the left. This is 36 units going to the right. So if I ask you, well, the absolute value of what number is 36, well, you would have to give me both answers because you don't know if it was a positive 36 or if it was a negative 36. So you end up giving both answers. So what we say is that the absolute value of x equals c, where c is greater than 0, c is a positive number, then x equals c, or x equals the opposite of c. So whenever we solve absolute value equations, we have to set up two equations. If we had the absolute value of 2x minus 1 equaled 5, well, we don't know if the number inside this absolute value bars was positive 5 or negative 5. So we're going to set it up to both. It was either positive 5 or whatever was inside was equal to negative 5. Then we will solve. We'll add 1 to both sides and divide by 2. So x is 3, or we'll add 1 to both sides. Well, negative 5 plus 1 is negative 4. Divide both sides by 2, x equals negative 2. So we came up with two solutions. If we check them, 2 times 3 is 6. 6 minus 1 is 5. Absolute value of 5 is 5. 2 times negative 2 is negative 4. Minus 1 is negative 5. The absolute value is 5. So it checks out. As we do this and we're solving, we want to make sure we have just the absolute value on one side before we set it up into our equations. If we had 4 times the absolute value of 1 minus 2x minus 20 equals 0. Well, before we set up our equation to solve, we have to get this absolute value portion by itself. It's just like if this were the equation 4x minus 20. We would need to get the x by itself. So we first of all solve for the absolute value. So that means we're going to add 20 to both sides. Now we have a coefficient, so we'll divide both sides by 4. And that gives us the absolute value of 1 minus 2x equals 5. Now we're ready to set it up into two parts. Either 1 minus 2x equals 5 or 1 minus 2x equals negative 5. Either what was in our absolute value bars was positive 5 or it was negative 5. Then we can solve. We will subtract 1 and have negative 2x equals 4. Divide by negative 2, so x is negative 2, or we'll subtract 1. Now negative 5 minus 1 would be negative 6. Divide by negative 2, and we get x is positive 3. Okay, if you just wanted, we wanted to check these. Now when we check it, we always go back and substitute back into the original. So what we would have here would be 4 times 1 minus 2 times negative 2 minus 20 equals 0. Well, that gives us 4. This is going to be 1 plus 4, which would be 4 times the absolute value of 5. Whoops, that's an absolute value bar, not a parenthesis. Which would be the absolute value of 5 is 5, and 20 minus 20 is 0. So that one checks out. If we did this other one, it would be 4 times 1 minus 2 times 3 minus 20. We would want to know, does that equal 0? So that's 4 times 1 minus 6, which is 4 times the absolute value of negative 5. Absolute value of negative 5 is 5. And again, we have 20 minus 20, which is 0. So it checks out. So you take your absolute value, what's inside your absolute value bars, and you set it equal to the positive and equal to the negative. But you want to make sure that you get your absolute value bars first alone first. If you start trying to solve this by not removing your absolute value bars, uh, you're going to have difficulty. If up here you try to solve and you keep the absolute value bars, you're going to have difficulty. You must remove the absolute value bars before you can solve, and you set up two separate equations and solve each one of them. All right, these are some different ways then that we have of solving polynomial equations. Uh, and the next thing that we will look at in the next lesson will be solving our inequalities.